Hello, everyone. My name is Suha Soilu, and I am the Director of Operations at Hosokawa Micron Powder Systems. We at Hosokawa Micron Powder Systems welcome you and thank you for attending our next in a series of educational webinars entitled Innovative Formulation Methods and Size Reduction Principles for Dry Powder Inhalers. Let me point out, if you have a question during this presentation, you may submit your question online at any time. Please refer to the Q&A pane on your screen. At the conclusion of the webinar, we will try to accommodate all of your questions during our question and answer forum. Hosokawa Micron Powder Systems is a division of Hosokawa Micron Group with headquarters in Osaka, Japan. We are the global leader in powder processing equipment with over 1,500 employees worldwide, production facilities in 5 countries, and 12 research facilities and state-of-the-art test centers. Hosokawa Micron Powder Systems, founded in 1923 under the name of Pulverizing Machinery, is responsible for the North American market. We, from our Summit, New Jersey office, provide full sales, engineering, manufacturing, and aftermarket services for the food, pharmaceutical, chemical, and minerals industries. We are proud to be the inventors of the micropulverizer hammer and screen mill, as well as the most versatile air classifying mills. Our brand names include Micro, Alpine, Reconauta, Majak, Micron, Stott, and Vital Air. At this point, I would like to turn the presentation over to Ms. Sylvia Broline, who is the Food and Pharmaceutical Division Manager at Hosokawa Alpine. Sylvia?
Yes?
You may start, and if we have any issues with moving the slides, just let us know.
Okay, I'll try. Thanks for the introduction, Suha. Hosokawa Alpine has been founded in 1898, and we are located in Augsburg, South Germany. We are specialists when it comes to powder processing, and within the Hosokawa group, we are the experts when it comes to size reduction. We design, engineer, and manufacture our equipment in Germany. There is also a separate division that engineers blown film lines in Augsburg. So let's start right away with the actual presentation about processing dry powder inhalers. I try to turn the slide, but I'm not sure whether it works.
Let's do this.
No, we have a small problem here. Will I try again?
You know what? Yeah, here we go. Are we all set? Got
Okay, I'll do it. Okay, fine.
Yep.
Okay, so let's start and hope it works. Dry powder inhalers are typically a composition of a carrier substance and an active pharmaceutical ingredient. Sometimes required are additives to enhance product properties such as flowability or additives to support the mechanical bonding of carrier and API. The carrier material, very often lactose, represents a high proportion of the final product and is often required to be of coarser particle size in the range of, let's say, 40 to 200 micron. The active pharmaceutical ingredient is only a very small percentage of the actual inhaler and needs to be of finer particle size, mostly in the single-digit micron range. APIs are very often cohesive, bad-flowing powders, and sometimes are a really tight or require a really tight particle size distribution. Special attention has to be paid on the amorphous content of the API. These requirements need special attention when it comes to choosing the suitable micronization or particle size reduction technique. The actual formulation of the carrier and the ingredient is done by intensive mixing or mechanochemical bonding. This presentation covers the different grinding techniques as well as the formulation techniques for inhalers. Particle size is the single most important design variable of a DPI formulation. This is taken from a paper that was given by Mr. Telko and Mr. Hickey, dry powder inhaler formulation. Like in any other drug production, the actual manufacturing process, including crystallization and drying, cannot be sufficiently controlled to achieve the required particle size. Therefore, additional steps, in some cases only deagglomeration after the dryer, or real grinding needs to be added to get the right particle size for inhalation. I think there's a slide problem. I clicked too many times on this. Okay, here we go. Sorry for that. Why is particle size? I think we missed a slide out here. I'm sorry again for the problem. Let me try again to go back. Okay, here we go. Sorry. Why is particle size, or why does particle size play such an important role in the production of inhalers? Extra fine particles, for example, improve lung delivery, and the particle size plays a crucial role in the bioavailability, the solubility, and the dissolution properties of drugs. Since dry powder inhalers are low-dose drugs, the content uniformity is of extreme importance, and proper control of the particle size distribution is a key factor for content uniformity. Dry powder inhalers are often delivered as aerosol suspension in a propellant, for which, again, the proper PSC is crucial. To choose the suitable milling equipment, it's required to characterize the different powders to be processed. Product properties such as hygroscopicity, flowing properties, bulk density, etc. have an influence on the suitable type of mill. And of course, it's required to know the actual starting size of the feed material after the dryer, for example, because pre-crushing or deagglomeration might be required before the actual fine milling of the powder. This is an overview of the different mills typically used for fine milling APIs and the carrier material. In a second part, we will present techniques for the formulation of DPIs, and we will start with an explanation of the different mill types and introduce applications, benefits, and limitations of each equipment. We'll start with the typical equipment used for micronization of APIs. The most common chet mill used in pharmaceutical industry for micronization of very fine particles is the spiral chet mill, or so-called pancake mill. Shown here is a sketch of a typical spiral chet mill with its internals. You can clearly see the feed injector for product supply at the top of the grinding chamber. At the outside of the grinding chamber is the air ring manifold, which allows the compressed air or gas to be distributed to the nozzles. The grinding gas is injected through a number of nozzles, you can see here, typically tangentially positioned at the nozzle ring. The fines outlet is at the center of the mill. The particles fed to the grinding chamber are accelerated by the high gas flow, typically in the range of 4 to 8 bar G pressure, and particles are crushed by collision with each other as well as partly at the walls of the grinding chamber. The fine particles are subject to the drag force of the air or gas flow and are drawn to the center of the grinding chamber. Although spiral chet mills have almost vanished completely in other industries and have been replaced by more controllable fluidized adipose chet mills, they still have a number of huge advantages for pharma applications. Due to the fact that there are no movable parts and they got a clear and simple design, no drives, etc., they are relatively easy to inspect and to clean. In general, chet mills do not create heat during grinding, which is an advantage, and since most pharmaceutical powders are somehow heat sensitive. And due to the above points, maintenance of those mills or operation under contained conditions is rather simple. The simple design of spiral jet mills comes with a number of disadvantages and limitations. Feeding is generally realized via an injector, and that means a narrow product feed inlet diameter to the mill, which limits the size of particles that can be actually fed to the mill to some single millimeters. If the product has agglomerates, typically achieved after the dryer, a pre-crushing step, for example in a conical screen mill, is required before actually feeding to the spiral jet mill. The biggest disadvantage of a spiral jet mill is that they are very sensitive to changes in feed material. If size and properties of the feed material changes, then the final particle size will vary accordingly. The relatively small geometries of spiral jet mills are as well often a limiting factor when processing sticky or adhesive products. The two photos show typical build-ups created by sticky products. It is then often required to stop production after a certain while and clean the mill before continuing. Build-ups like this also change airflow patterns and speed inside the mill and can therefore have an influence on the end fineness. One issue with spiral jet mills is that the particle wall collision can be very negative when processing abrasive materials. This effect is not so often seen with pharma products, but if the products are abrasive, then this can be a major problem. Spiral jet mills can be made of different materials of construction or lined with materials such as polymers like PTFE or ceramics to improve problems with stickiness or abrasion. The lower photo shows, for example, a mill with a PTFE insert, but for that product, this has not been the right solution, as can easily be seen. Finally, spiral jet mills are rather difficult to control because unstable feed rates, build-ups, etc. have an influence at the flow pattern in the mill and therefore the final particle size. The following graph shows a typical particle size distribution achieved on a spiral jet mill. What's characteristic for the spiral jet mill is the small proportion of oversized particles which are typically able to leave the mill more or less unground because there is no classifier installed in that mill apart from what we call a static classifier. Spiral jet mills come in many sizes and depending on the required capacities or batch sizes. The left-hand picture shows a typical size of a small production unit. The spiral jet mill in that picture is a diameter 140 millimeter, which gives typical capacities in the range of 5 to 10 kg per hour. The complete system is a very simple setup, consists of a feeding unit, in this case a twin screw feeder with an agitator, feeding directly into the injector of the mill. The fine product dispersed in air gas is conveyed to the automatic filter, where the product is separated from the airstream and discharged through a simple manual flap valve into a container. The container is not shown in this stage. There is a HEPA filter installed after the automatic filter and a blower which is installed in a technical area not shown on the photo. The blower serves for conveying the process air. As you can see, the installation of a spiral jet mill can be rather compact and is therefore again an advantage because it's easy to clean. The actual photo shows a unit that is also sterilizable. Feeder and mill can be sterilized in an autoclave, completely mounted on the movable frame there, and the filter can be separately sterilized on its frame. This illustration shows the principle of a fluidized bed-opposed jet mill with an integrated air classifier. But before we go through the advantages of those kind of mills, let's look at the actual operating principle. This slide shows the bottom section of the fluidized opposed jet mill with the grinding nozzles. Contrary to the spiral jet mill, the nozzles focus in one point and compressed air gas is applied at pressures in the range of, let's say, 3 to 10 bar. The product is fed to the mill gravimetrically and falls into the actual grinding chamber. There the particles get accelerated by the fast gas stream, and grinding takes place in the center of the mill by particle-to-particle collision. The particles are offered to the integrated air classifier. This classifier is driven by a frequency converter, and the speed can be steplessly adjusted. The air gas flow has to go through the shown lamellas of the classifier wheel. The particles are subject to two forces, the drag force of the air and the centrifugal force of the classifier wheel. Fine particles are risen with the air, whereas coarse particles are rejected by the classifier and drop back into the mill. High classifier speed means fine end product, low speed means coarser product. Can be adjusted, as said, steplessly. These classifiers are typically suitable for finenesses in the range of, let's say, 5 to around 150 micron. Anything else in between can be adjusted. I think the explanation of the working principle leads automatically to the advantages of those kind of mills. With the integrated air classifier, it is possible to exactly adjust the end fineness, and such a mill is much less sensitive to variations in feed material. Due to the fact that grinding takes place by particle-to-particle collision, there is no contamination and no wear. Typically, those mills create a steeper particle size distribution because the particles will leave the mill almost immediately if they can pass the classifier wheel. Feeding can be realized through an airlock. Therefore, these kind of mills are not sensitive to agglomerates in the feed material, etc. Looking at this graph, it shows a typical particle size distribution as you get it from a fluidized bed-opposed jet mill. Looking again at the top end of the particle size distribution, the integrated air classifier clearly provides a sharp cut at the top end of the PSD. There are a few disadvantages when it comes to opposed jet mills. These are the higher investment costs and the higher cleaning effort, and also more sophisticated controls are required. In other industries, opposed jet mills with integrated classifiers have long replaced spiral jet mills. The photo shows an opposed jet mill size 100 millimeter with a classifier wheel of 50 millimeter. This size represents already a small production unit for capacities in the range of 1 to 10 kg per hour. If you compare directly fluidized bed-opposed jet mill and spiral jet mill, have a look at this graph. It shows the PSDs of both types of mills with the same product. Again, you can see on the top end of the PSD, the integrated classifier allows to produce a steeper PSD with a sharper top cut. To optimize the micronization step for APIs, it's important to properly control the feed rate. This is especially important with spiral jet mills that are much more sensitive for variations in feed rate. Variations in grinding pressure will also lead to deviations in the end fineness and therefore need to be properly controlled. For DPIs, the process gas quality can be crucial, specifically the moisture content. The moisture content not only has an influence on the actual flowing properties, stickiness, electrostatic charge of the powder, etc., it can also influence the creation of amorphous content, and therefore on possible recrystallization in the following processing steps. Last but not least, when it comes to determining the suitable mill type, the suitable method of powder sampling and particle size analysis is as well very important. This leads us to the next part of the dry powder inhalers, the carrier material. Carrier material is often lactose. To achieve the required properties such as the optimum flowability, the particle size distribution is, for the carrier as well as for the API, crucial. Depending on the type of applicator, the optimum fineness might be in the range of 40 micron or can be up to 200 micron. High content of fine dust is normally not allowed, and therefore the production of the carrier is often a combination of milling, classifying, and sometimes blending step. I start with the more simple mill used for carrier material. The fact that carrier material is mostly coarser than the actual API requires typically a different mill type. The graph shows a mechanical impact mill. The material is gravimetrically fed to the mill. The installed beater accelerates the particles, and they are crushed against an integrated grinding track or screen. As an alternative, those mills can be equipped with pin discs, which we'll show at one of the next slides. The beater works as well as a blower and creates airflow. This airflow pneumatically transports the material to the subsequently installed filter, where the product is separated. And additionally, the airflow cools the product. Nevertheless, mechanical impact mills do create heat, and there is a typical temperature increase at the milling step. It's ranging from single digits up to, let's say, 20-25 degrees Celsius. The difference between the former shown fluid energy impact mill is that the speed to which the particles get accelerated is much lower, and therefore the achieved particle size is coarser. Circumferential speeds of those kind of mills are in the range of maximum 120 to 150 meters per second. Those mills are suitable for medium range finesses, and the advantage is that they can be equipped with a number of different grinding tools suitable for different products and requirements. The picture at the right hand shows one of the very typical grinding tools used in pharma industry, pin discs. There is one rotating pin disc and rotating in the housing, and one static pin disc at the door. Compared to beater discs, in combination with screens, etc., pins actually deliver the highest possible fineness, but cannot use if the material is too heat sensitive or very abrasive. As an example, pin mills are used for fine grinding of lactose. The typical finesses are then D97 of 200-300 micron, and the typical maximum fineness with lactose and pin mills is around 90% below 75 micron. When steeper PSDs or higher end fineness is required, then an impact mill with an integrated air classifier might have advantages. As we have earlier seen with the jet mills, a typical mechanical impact mill can also be combined with an air classifier. The operating principle is similar. The bottom section shows the impact mill with the beater and the grinding track. The top section is equipped with an air classifier. Airflow is created by a blower and sucked through the system through the grinding zone and through the classifier out of the system. This airflow transports and cools the product and offers the particles to the integrated classifier. Again, the fine particles can leave the mill, and the coarse particles are rejected and dropped back into the mills. By adjusting mill speed, classifier speed, and airflow rate, there is an optimum control of the achievable end fineness and particle size distribution. For example, low mill speeds and high airflow rates lead to a steep particle size distribution. There is a comparison between a typical impact mill and the classifier mill, and it clearly shows the difference of the integrated classifier. There is an optimum control of the top size, since no oversized particle can actually leave the mill. And looking at the particle size distribution, inhalers should as well not have a high content of very fine dust, because this very often leads to a second classifying step to remove the very fine end of the particle size distribution. We have already introduced the operating principle of an air classifier in combination with different mills. These air classifiers can also be used for the separation of powders. For the production of carrier material, there is often a classification step after the actual milling step. The principle is more or less the same. The material is gravimetrically fed to the classifier from the side or from the top. There is an airflow created by a blower. The feed material will be dispersed in air or gas and then offered to the actual classifier. The coarse material will then be rejected by the classifier and will drop to the bottom, where the coarse fraction is collected. Oh, I'm sorry, I clicked too much. Sorry. The coarse product is collected underneath the classifier, and in our case, the coarse product here is then the final product, and the fine fraction will leave the classifier and is separated at the filter and is then used for other purposes or is waste. This graph shows a typical classification process after grinding and micronization step. The ground material is fed to that classification step, and the blue graph represents the coarse fraction after the classification, in this case our final product, and the red curve represents the fine fraction, in this case waste. The original fine content in the feed material after the micronization, let's say at 40 micron, is in this example reduced from originally 30% to around 5%, as we can see here. To summarize the size reduction part of the presentation, both carrier material and API need a very specific particle size distribution, which leads to the different grinding technologies required. We hope we were able to provide you with a good overview of these techniques. The second part of our presentation is the actual formulation of dry powder inhaler by high share mixes. This slide shows the process associated with DPI powders in order to achieve the proper transportation, storage, and dosing of small amounts of API particles into the patient's respiratory tract. As mentioned in earlier slides, the finely ground API is blended with the carrier particles, the so-called excipients, which are prepared to have a defined surface area and surface energy. To achieve an even layering of API particles, an appropriate blender with the correct operational parameters needs to be selected. This allows for the proper handling of the APIs, which is typically a cohesive powder and normally a fairly difficult to work with, especially in the smaller quantities that are needed. In the final dosing stage, the formulated particles will allow separation of the API into the single particles, resulting in micron-sized therapeutic dosage being able to reach the required depth in the lungs. These are some examples of scanning electron microscope images of different types of formulated materials, where a uniformly distributed layer of API particles loosely attached to the surface can be seen. The mixing technology used would have to apply regardless of the API's crystal structure and whether it has spherical particles or high aspect ratio. DPI powder characteristics, which are relevant to the quality and performance of the formulation, include certain aerodynamic properties like particle size, density, and shape of both formulated particles as well as the API. Also, the phenomena related to the interaction between the carrier particles and the API play an important role in the final quality of the product. The blending properties and surface characteristics of the carrier particles, which will affect the bonding between the API and the carrier, the flowability of the formulated material, as well as the fluidization properties, together with the entrainment and separation characteristics, determine the physical behavior of the formulation in the inhaler device. In order to obtain the right formulation, a balance has to be found between sufficient mixing energy actually required to disperse the API as single particles between the bulk carrier particles, and on the other hand, the mixing energy cannot be too high, since this could lead to possible damage of the carrier particles, resulting in undesirable variations in the product characteristics. Similarly, the bonding of the API particles onto the surface of the carrier particles has to be sufficiently strong to form a stable formulation. Just as above with the mixing, the bonding strength has to be such that while providing the proper handling characteristics, it also needs to be capable of releasing the API while being inhaled. Hence, this requires a dedicated mixing process, as well as a proper selection and manipulation of the powder properties associated with the DPI formulation. The most important powder properties we have available as a tool to optimize the formulation are the interparticle forces. These forces affect the interaction between the API and the carrier particles, and the proper balance between the sufficient bonding and separation is a matter of controlling these interparticle forces. Most important examples of these forces are van der Waals forces, surface energy, electrostatic forces, and the hygroscopicity of both of the particles. In order to manage all these different interparticle forces, a good control over your blending process is essential and will widely affect the choice of the blender to be used. In order to understand the principle of a dry powder blender, the different mixing mechanisms will be illustrated. First is the overall mixing mechanism, which takes care of the distribution of one component within the other. Key here is to be able to transport the particles throughout the mixture. An optimal mixing is achieved when the different components can be randomly distributed. This process of mixing powders is suitable only for free-flowing powders which do not possess any significant interparticle forces, allowing the particles to move freely amongst each other. Excipients, which generally have a coarse particle size distribution, are a good example of a free-flowing powder. APIs, on the other hand, are a typical cohesive and much more difficult to mix. Due to the relatively strong interparticle forces, these powders cannot move freely and will then therefore form agglomerates. In this case, the mixing of such powders require not only transportation of particles, but also some extra energy to break up the interparticle forces. Therefore, mixers for cohesive powders are often called intensive mixers. The most common used mechanism for the intensive mixing of powders is the impact mechanism. Here, shown, a knife-type tool literally cuts through the agglomerates associated with cohesive powders to form smaller fractions. Although very efficient in dispersing the fine cohesive particles of the API within the coarse matrix, this mechanism does not really lend itself to providing an acceptable coating of the coarse carrier particles. For this, it is better to use a shear mechanism, where the dry powder is subject to frictional forces, resulting in a rolling action of the particles and hence the separation. Both the coarser as well as the finer particles will be subject to the rolling action, allowing for a very effective coating process. One such mixer which combines both intensive mixing mechanism is the cyclomix. A top-driven rotor has both a set of knife blades for the impact mixing as well as sharing pedals, which will allow for controlled share and impact of the DPI formulation. In fact, by controlling the speed of the rotor, both effects can be separately controlled. The material to be mixed will be centrifuged by the rotation pedals, causing the mix to rise along the walls of the conical-shaped mixing bowl, while the domed cover redirects it back down to the center. The shear forces along the walls will result in intensive mixing, when combined with the circulation pattern outlined above, will produce a rapid overall mixing time. With increased rotor speeds, larger amounts of material will be forced up to the top section, where the product subjected to the knife blades will produce higher impact energy relative to the shear forces applied. Additionally, efficient cooling and heating of the product can be accomplished via utilization of a jacketed vessel. Effective heat transfer will take place due to the application of the heating or cooling energy and the exact shear zone, which will also result in a very accurate temperature control of the formulation. All the required effects for the formulation can accurately be controlled by the adjustment of rotor speed, paddle angle, paddle gap, and process times. Since there are multiple variables utilized, a matrix structure with the extreme conditions that are verified during testing can provide the basis for proper combinations required. Optimization of the process can be achieved utilizing interpolation of the matrix data while keeping an eye on the side effects, like breakage of particles at extreme high speeds and or temperature development at extended processing times. Unfortunately, due to the confidential nature of every customer-specific formulation, we are not able to provide operational data associated with DPI powders during this presentation. Yet, to demonstrate the discussed effects, we can share following examples. The examples are a little slow. In this slide, we can see resin particles that were treated with a combination of temperature and shear, and due to the rolling motion inside the cyclomix, resulted in producing rounded particles. This effect can be significant for DPI powders, since the rounded particles will improve the flowability of the end product significantly and possibly release characteristics of the surface coating. The second example here is another illustration of a good coating performance achieved with the cyclomix. Here, a fire extinguishing powder was treated with stearates in order to make it water repellent. Deficient or non-uniformity of the stearate coating over the carbonate surface will cause the powder to absorb water and dissolve rapidly, like on the left side. However, the photo on the right shows that with the uniform coating achieved with the cyclomix, the material is unable to mix with water and precipitate to the bottom, leaving clear water in the container. To summarize the advantages of this high-intensity impact and shear mixer, there's a perfect dispersion of fines due to the combination of impact and shear mixing. We got an accurate temperature control due to the jacketed vessel. The rounding off or densification of particles is possible, and there is a single layer coating achievable with the cyclomix. We can create homogeneous mixture without any lumps, and the whole process is extremely reproducible. With the conical design, vessel filling rates can be allowed between 30 to 100%, and we can fully discharge through the central bottom discharge valve. And there is CIP and SAP designs available as well. And that's all from my side, and thanks for the attention.
I wanted to thank Ms. Sylvia Berlang for this great presentation, and we'll start to take some questions. First question, Sylvia, is from a customer that says we have very small quantities of materials that we would like to do development work on, and what is the smallest size cyclomix available?
Okay, typically cyclomix is available in the sizes from around 1 liter up to 1,000 liter product volume, and we have recently introduced a new pico line where we have added a very small lab scale cyclomix of 0.1 liter to allow trials with a very few gram of material. Actually, the small scale applications are not only interesting for the cyclomix. We have introduced recently a whole pico line, we call it, where we have all our equipment more or less at very, very small scale for sometimes amounts of less than 1 gram up to 10 gram. These are available systems are spiral jet mills, opposed jet mills, classifiers, wet bead mills, etc., all under the marketed line of pico line, let's say.
Okay. Here's another question, again on the cyclomix. What is the basic scale-up parameter for the cyclomix?
Okay, there are two primary scale-up parameters, and this is the processing time and the rotational speed. That means the actual rotor tip speed. And this can be rather good scaled up between the 1 liter and the 1,000 liter cyclomix.
You had mentioned, here's another question, you mentioned the creation of amorphous content during micronization. Do you know what milling parameters have an influence on this?
Yeah, we have done extensive test work together with some of our customers in varying grinding pressures and the applied specific energy, etc. And we have also experimented with the humidity of the process gas and know that there is a big influence of that. We have the possibility to carry out trials in our test station with humidified compressed nitrogen, for example, in order to improve the creation or to limit the creation of amorphous content. But unfortunately, in our test station, we are not able to measure the actual amorphous content, and we cannot share the results that we get from other customers.
Okay. What is the typical process times and associated temperature rise with the DPI powders in the cyclomix?
Okay, I mean, in a cyclomix, 5 liter, let's say, the typical process times, they range from 5 to 15 minutes, depending on material, as usual, and speeds chosen. With the typical rotor speeds associated with the dry powder inhalers, there should not be any change in the temperature. Although, as mentioned earlier, the units can be supplied with jackets for cooling if that is required.
Okay. There was mention of the gravimetric feeding of jet mills. Does that mean you suggest loss in weight feeders with jet mills in general?
Yeah, typically this depends on how tough the specification of the product is. With spiral jet mills, we certainly are in favor of loss in weight feeders, since spiral jet mills are much more sensitive when it comes to variations in the feed rate. Actually, the feed rate is, apart from the grinding pressure, the most important parameter to adjust the end fineness of a spiral jet mill. With opposed jet mills and the integrated classifier, the feed rate is not an adjustable parameter, it is a dependent parameter, and we would rather adjust the optimum filling level at a certain end fineness, and then we achieve a certain capacity. So yes, loss in weight feeders with spiral jet mills, but generally not required with fluidized bed opposed jet mills.
A customer here is saying that they use a spiral jet mill in micronizing their products and have ran into plugging problems with the feed eductor. Is there a way to eliminate this?
Yeah, this is, as mentioned earlier, this is a typical problem for spiral jet mills. The small inlet diameter of an injector is prone to block up with difficult materials, specifically with sticky or adhesive powders. To overcome some of those problems, we have used different materials of constructions, such as PTFE or similar materials, but we have also equipped some of our larger jet mills with pressure sensors at the injector to detect if the pressure drops and allow for cleaning before we actually run into that typical blowback problem.
And I guess we'll do one more last question, since we're kind of heading into the past the 45-minute mark. Does the method of feeding of the ingredients into the cyclomix have an effect on the outcome?
Oh yeah, definitely yes. The optimum way of charging the unit is to sort of sandwich the API between the excipients. If all the API in the bottom is in the bottom, then this will lead to some unmixed API in the bottom. If all the API is fed to the top, then this will lead to sticking of the material to the cover. So again, we would like to sandwich the API between the excipients.
Okay, well, I want to again thank Ms. Sylvia Broline for this informative presentation. And I just want to remind our listeners here that the webinar, as we did it, will be posted up on our website in the Education Center at the Hosokawa Micron Powder Systems website, probably no later than tomorrow morning. And feel free to inform your colleagues about it, that they can come and watch it at our website. And I want to say thank you for joining us today, and we'll keep you posted of the upcoming new webinars.